Hi, my name is Joe Tavares. In this video we discuss the design of no back EMF motor. No back EMF motor. The meaning of the logo will be explained at the end of the video. So a motor, you apply magnetic field, you apply a current, and you get force, mechanical energy. In this case it's circular force. Converts electrical energy directly to mechanical energy. So here's the design, and we have 4 induction coils. They go in between the green cores into the page. Here showing the current coming out of the page. It goes across and into the page on the side. Same thing here, it comes out of the page into the page here. You notice that the cores, there's an air gap here, and these black arrows, this is the field produced if you apply the right hand grip rule. The field produced by the induction coil is in the same direction here, but opposite direction on this side. So the force is from left to right here, and it can go around, and you see the left here is downwards, the left here is from right to left. So it's a circular force. So there's large air gaps for the magnetic path on the induction coils. No air gap for the magnetic path for the B core. So the B coils are these red square blocks, the envelope of it, and you have 4 quadrants, and they all no air gaps on the quadrants. So there's the design of it, showing the design. These are the B field coils. There's the vertical, it's actually two coils, half of one, half of the other. Here with taking the top cover off to show the induction coil going down to the bottom. So the fields are orthogonal to each other, no interaction. So the induction coil here, the current is coming out of the page, produces a field which is in red, H field in red, and also the path, the magnetic path, sees two large air gaps. And but the B field coil produces a B field coming down on both sides here, and you see the magnetic path here. There's no air gaps for the black arrows, the B field coil, B field. Here the current is into the page and produces a red field which is circular, which has large air gaps. Here the two add up, so the force here is up. Here the two add up, here the two cancel. The force is from left to right. Also, you notice there's no interference between these fields and these fields. Here the field is from left to right, from right to left, and here is vertical. They're at 90 degrees to each other. So these fields do not interact with these fields. That's why I place 4 of them, so that they are at 90 degrees to each other and they don't interfere with each other. These fields are orthogonal to each other and no interaction force can occur. So calculations. So the radius from the center to the middle of the coil, the induction coil, is 100 millimeters. Also, there's an additional 25 millimeters from the center of the coil to the middle of the core here. So L mean is the mean length depth of the coil. Now, going to the page, which is not, you can't see here, the depth of this coil, the length of the coil is 200 millimeters. That's chosen. Maximum outside diameter of the motor is 300 millimeters. This is diameter, so it's 125 by 150, so double 300 millimeters is maximum outside. So this is the induction coil. Now this is like a right angle triangle. So the length from here to there, the path across the top and bottom is 1.4 times 100 millimeters. So the induction coil magnetic path has two air gaps, and each air gap is 40 millimeters. So 80 millimeters in air. The B-field coil magnetic path is 2 times R plus 25, which is this radius here, which is 100, plus 25 from the middle to the middle of the core, plus 1/4 of the circumference of this large circumference, which is 1/4 of 2 pi R 125, because the radius from here to there is 125. So it comes up to close to about a half a meter is the magnetic path length of the core. Core depth is 200 millimeters. This core thickness here is 10 millimeters. F equals LIB. L is the length, is the induction segment of the induction coil. L mean is 200 millimeters induction segment on one side of the induction coil. This induction occurs on two sides of the induction coil. So L is 2 times L mean, which is 400 millimeters. We choose B to be 1 Tesla. So power is torque times angular speed. Power equals torque times W. W is 188 radians per second at 1800 RPM. Torque equals force times radius equals force times R mean. So force equals current times length times B field. Power equals, so we substitute power equals force times R mean times W equals ILB times R mean W. At 1 Tesla, W at 188 radians per second, and L equals 400 meter. We substitute those values and we get power equals 7.5 watts per amp times the current. So it's 7.52 watts per amps times whatever current we decide to put in induction coil. Sorry. We choose the induction coil to fill the air gap. The air is then 40 millimeters by 40 millimeters. Using 1 millimeter diameter wire, the number of turns N is 40 by 40, which is 1600. We choose N to be 1400 due to percentage loss in filling the area. In each gap there are 2 vertical sections of an induction coil. Therefore N for one coil is 700 turns. So because the air gap is actually 2 halves of one coil, so 700 turns here, 700 turns, the total is 1400 turns, and the width is 140 millimeters, and from the center to here is 100 millimeters. The depth is 200 millimeters, is the segment length where the induction occurs. The induction is on 2 depths of the coil, therefore L is 400 millimeters. The formula for FILB. Depth 200 millimeters, width is 140 millimeters. The induction coil length for one turn is 2 times 140 times 200 is 760 millimeters, or 0.76 millimeters. So this is the length of one turn for the induction coil. The total current in one induction coil is N times current. 700 turns times 1 amp equals 7 amps. That's from one coil. There are 4 induction coils. The total current is 4 times 700 is 2800 amps. We need to ensure that the B field induced in the core by the induction coil is less than 1 Tesla. Should be less than is less than 1 Tesla to ensure that it will not saturate the core. We want the B equal to or less than 0.1 Tesla. The total air gap for one coil is 80 millimeter. In air at 0.1 Tesla, H is 80 ampere turns per millimeter. For 80 millimeter air gap, the current is 80 times 80 is 1600 amps. So we are okay since 700 amps is less than 1600 amps. From previous calculation, power equals 7.2 watts per amps times the current. So 7.2 times 2800, which is the total current, gives you 21,056 watts. We run it off to 20 kilowatts. The mechanical power output is equivalent to 20 kilowatts. The power consumption of the induction coil calculations. The length of one turn from previous slide is 0.76 meters. The total length on coil is N times 0.700. That's for one coil. 700 times that is 532 meters. The length on the four coils, you multiply by 4, it gives you 2.13 kilometers. The resistance of 1 millimeter diameter wire is 20 ohms per kilometer. The total resistance of the four coil is 20 ohms times 2.13 kilometers, which gives 42.6 ohms. So the power consumption or dissipation is I squared R, which is 1 amp squared times 42.6 ohms, which is 42.6 watts. Run it off to 45 watts. Power consumption of the B field coils calculation. From the previous slide diagram, the B field coil magnetic path length is 446.25 millimeters or 0.446 meters. It's about a half a meter. Using steel 1008 core from the BH curve for B equals 1 Tesla, the H is 130 ampere turns per meter. So the total ampere turns, the number of ampere turns required is 130 times the magnetic path length, which is 60 ampere turns. From previous slide diagram, the B field coil width is 80 millimeter and the depth is 200 millimeters. The length of one turn of the B field coil is 2 times 80 plus 200, which is 0.56. The total length of one coil is 33.6 meters. For total length for all four coils is 134.4 meters or 0.134 kilometers. The resistance of 1 mil diameter is 20 ohms per kilometer. The total resistance of the coil is 2.68 ohms. Power consumption is I squared R, which comes to about 3 watts. So the power consumption of the induction coil and the B field coils together is about 48 watts. So we run it off to 50 watts. So this device, now to prove that it is only can operate as a motor and not as generator, this device cannot operate as generator, no flux cutting and no flux linking on the induction coil while it's rotating. So first, there's no flux cutting because there's no B field in the slot. And as far as flux linking, due to the slot edges, the edges are close together and parallel to each other. The pair cancel and the flux link cannot occur. No B field exists inside the slot. Flux cutting cannot occur. So there's the rotation, and likewise for everything they cancel. Size and volume calculation. Outside diameter is 300 millimeters. Depth is 200 millimeters or 20 centimeters. R is 150 millimeters or 15 centimeters. Volume is pi r squared times the depth, which comes to 14,130 cubic centimeters. In cubic feet, you multiply by 30, or you divide by 27,000, you get about half a cubic foot. Weight, density of copper is 8.896. The density of steel is 7.872 grams per centimeter. Use an average of 8.5, so the weight came to about 120 kilograms. A non-magnetic material is in the shape of a cross attached to the shaft to hold. So there's a lot of openings in there. We need to fill it up with some non-magnetic, some non-electrical material to hold everything in place. And so the calculations for 120 kilograms could be much less because the density of the filling materials will be much less than of that of steel or copper. The outer aluminum sleeve protects the induction coils against the centrifugal force. So we put the silver sleeve here to hold, but also we need to put filling material in between to hold everything. Need to add filling material around the B field coils to protect against the centrifugal force. Slip ring connector. Slip ring connector is an electromechanical component that provides electrical connection between rotary and stationary parts of the machines. It's also called the rotary electrical connector or rotary electrical interface. Through bore slip ring is a hole in the center of the slip ring where the shaft is inserted into. It is normally installed by fixing the outer ring when the inner ring rotates. So the inner ring is the one that rotates. So this side is connected to the motor and this side is connected to the outside world. It does not rotate, it does not move. And there's the websites you can go to get more information. I just pick some out of the catalog. I don't have no particular preference. I don't even know what the costs are. But even Rotorcon has another series, I think it's GXS series, which is a high quality, high reliability. So you want to shop around for it. Now, the one I picked is the GT 1256 series, and the one I picked is the one that has, because the motor only requires very low current, only less than an amp for both the induction coil and for the B field coil. So I picked the lowest I could find was the one with 6 signals. So GTS 1256 SO6 operates up to 1800 RPM, induction coil, 1 pair at 5 amps maximum voltage, 440 volts DC. The B field coil, 1 pair at 5 amps max. So to mount the motor, you can mount it with the pillow block bearings. And here's how you put it all together. It's similar to the generator, but you only need a small. The cost of the slip ring will be much lower than the cost of the one for the generator. Only need 4 1 amp connection slip ring rotor. For the motor induction coil, you could arrange the coil as one coil 60 volts at 1 amp, or as 2 coils in parallel 30 volts at 2 amps, or as 4 coils in parallel 15 volts 4 amps. Don't need high voltage power supply. This way you can reduce the cost of the power supply. The slip ring signal contact can handle up to 5 amps. So you need a control system. So for the motor, you need a control system to control for motor speed to maintain constant speed under variable load conditions. Because there's no way the motor knows what the load is and what the speed is. So you need a control system. So you have the motor speed sensor, which is the feedback. You compare to a motor set point, which would be 800 RPM, and then you vary the current to the induction. In this case, I use the induction coil. You vary the current induction coil to maintain the motor speed at 1800 RPM. Alternatively, you may want to control the B field instead of controlling the induction coil current. The B field coil requires less than 5 watts, easier and more efficient. The only drawback is that you must provide constant 60 watts or 60 volts at 1 amp or 30 volts at 2 amps to the induction coil, even if there is no load. Motor speed control by controlling the B field coil current instead of controlling the induction coil current. Since the power consumed in the B field coil is less than 5 watts, a transistor may be used. So even though you may dissipate power in the transistor, but it's only going to be 5 watts maximum or 3 watts. Not concerned about the power dissipation and controlling, so mainly in the transistor. Again, this is the motor speed sensor. You compare it to it and you drive the current drive to the B field coil. So we come at the end. So the green motor, no back EMF motor. The size is 300 millimeter diameter, 200 millimeter long, 12 inches diameter by 8 inches long. Volume is about 0.53 cubic foot. Weight is 120 kilograms. It could be much less because there's a lot of empty space and it's going to be filled with material with the lower density. The output is mechanical power equivalent to 20 kilowatts. Power input consumption is 0.05 kilowatts. The logo represents the 4 quadrants of the motor where there is no air gaps in each quadrant for the B field coil and large air gaps for the induction coil in between the quadrants.